Hi guys, welcome to yet another episode of Vision Language Modeling series. This is season 1 episode 3A, so rather a new episode. This is an extension or addendum for the previous episode. In the previous episode, we built a multimodal facial recognition model using contrastive pre-training. To be precise, more than one models we built in the previous episode. What we're trying to do in this episode is to try to visualize the joint embedding space learned by the models in that we built in the previous episode, right? Why I'm doing this is I got some questions and feedbacks where people really wanted to have a qualitative feel of the model's lessons and they wanted to compare it with their intuitions, which is a fair request. So I thought I'll honor that request in this episode. And in terms of brass tacks, for those who are tuning in for the first time into this episode, it's a mandatory prerequisite for you to check out the previous episode because we are following up on top of that, and without the lessons and takeaways from the previous episode it won't make sense. So I encourage you to stop this or pause this and go check it out and come back here. And for those who have already watched the previous episode, let's get started. So yeah, even though you guys have already checked out the previous episode, I just would like to give you a quick recap as to what we did. And in terms of the notebook, 95% of the notebook has been borrowed from the previous episode because we are not trying to do anything new here. We are only going to take the models that we built in the previous episode and try to load it again and try to visualize the model's embedding space in this episode in multiple different ways, and there are a bunch of other things we're going to look at, right? So in terms of notebook, that's pretty much same, and I've borrowed only few stuff. So the recap is what we built in the previous episode is we wanted to have a model which can do a couple of things. One is cross-modal facial recognition or multimodal facial recognition. As you can see from the images, cross-modal face recognition is about taking a natural language query and then going to a face database and retrieving the faces. And multimodal facial recognition is about taking a combination of images and natural language query, going to a same face database and retrieving the faces, right? So this is what we saw, and just to give you guys a recap, and we are going to reuse this model and try to visualize, but for those who have already watched it, just a gentle reminder, we did some qualitative analysis in the previous notebook. If you have not checked it out, check it out again or refresh your memory. And we have also done some quantitative analysis of the model's performance compared with SOTA models and stuff like that, right? So in terms of data set, in terms of pre-processing it, model architecture, loading it, blah, 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 everything is going to be ditto. I'm going to cut to the chase and directly go to the part which is very relevant for this particular episode. Just to remind you, we built models with two different kinds of vision backbones. One is using transformers, that is VAT, and one is using CNN. In this episode, we're going to use the VAT version of it. Yeah, so that's what I'm doing here. So this is the first logical step, which is probably relevant for us. So where we are trying to take the VAT version of the model that we built in the previous episode, taking the checkpoint, which is which is the useful checkpoint, and then we are loading it. And then let me give you some background as to, if for those if you're an expert in visualizing embedding space, please bear with me. I'm just trying to do some justice for people who are absolute beginners who have not done any kind of work like this. Please hang on. When a model is built, you can do a bunch of things. You can do some random checkings, random testings, and then you can do some quantitative test. So the testing that you can do on top of the model's performance is classified into qualitative and quantitative. Quantitative is to empirically come up with the numbers and compare with other models to make a decision, right? Qualitative comparison is like I said, spot checking, or you have to present some the results to someone in some way, shape or form, right? So visualizing an embedding space, whether it is a giant embedding space or a simple embedding space, comes under the idea of qualitative testing of a model's performance. You can get the idea of what the model, you get a feel, instead of rather than running an expensive quantitative test, you can get a feel of what the model would have learned, what the model's intuitions are, what the model's blind spots are. You can get it. You can not only understand it, since it's a visualization, you can also present it to a stakeholder who is not really a technical person who is a business stakeholder who understands or probably will appreciate the understanding of a model. So there are a couple of different reasons why we want to do visualization as a qualitative test of the model's performance, right? So that's the idea. And in terms of how, right, we are trying to quickly cover the why and hows of it. In terms of how, right, so if you look at visualization as a step, what we are trying to do basically is go into embedding space and look at the models, embeddings, and how they are tied up together. But if you look at the model that we are using in this particular example, it is the VAT based model, but the vision embedding, the vision dimensions are 768, text dimensions are 768. Before we combine them to learn the joint embedding space, we projected it down to 512, right? Even though it is projected down to 512, for a human mind, visualizing anything more than 4 or 5 dimensions is pretty hard, right? So the first things in terms of brass tacks, the visualization first lesson is you obviously have to have some kind of a dimensionality reduction technique to reduce the dimensions where it is tractable for a human mind to visualize and make some genuine understanding of what's happening. So I love how everybody is thinking about PCA, and for obvious reasons, PCA has got some limit. It's good, it's useful, but it's got some limitations in terms of whether it is linear data alone, or if all the variants are captured only in the first 2 or 3 principal components, then only it's suitable. There are certain suitability issues in using PCA as an algorithm for dimensionality reduction. But there are other 2 techniques called UMAP and T-SNE, and we, there are a lot of, for the better use of our time, I'm not going to get into the details of the dimensionality reduction techniques itself. Since we're going to use UMAP for this particular episode, I've given you a link where Josh Strammers put in a great video about the basics of UMAP. Please check it out, and then you can continue here, or you can check it out later also, because not understanding UMAP is not going to, the details of the mathematical details of UMAP is not going to stop you from understanding what's happening here. But if you still want to go through that in whichever order you feel like doing it, right? And there are some basic differences in terms of UMAP is really fast and it maintains the global structure compared to T-SNE. There are a bunch of debates going on there. So hence, for a simple reason, UMAP is super fast compared to T-SNE. Hence, we are using UMAP in this particular thing, and I'll also show you it's how easy it is to extend it to T-SNE. So that's the why and how part of the actual visualization itself. Why visualize an embedding space, and Next is, in visualization there are a couple of different ways, right? Imagine you have a classification data set, right? In this case, it's a hobbies data set, and then you are looking at a 2-dimensional projection of the hobbies data set. The hobbies data set, let's say, imagine you have the description of the different hobbies and then the labels. The labels being books, cinema, cooking, gaming, and sports. Right? If you're having a label data set like this, projecting it down to 2 dimensions is going to basically show how they are clustered around the labels and how they're segregated and so on and so forth. It's a completely different way of visualizing it. It gives you a feel, and maybe you get to present it to some of the stakeholders, right? But the key thing that you want to notice is the descriptions of the hobby, which are projected in the 2 dimensions, are projected basically from single modal. It's only text, right? Or even if you see a unimodal image only visualization, it is still single modal. So the unique thing that we are trying to do here is we are going to have multiple modalities sharing the same embedding space. And when I say sharing the space, simply having a VAT model and a BERT model or a SOTA sentence transformer and encoding text and images and putting it in the same embedding space itself merely makes a shared embedding space. But that's not what we are looking at here. We are going one step ahead, and we have jointly trained the vision part along with the text part. So now what do I mean by that is, when we have loaded in the actual network, you can look at the trainable parameter, which is set to true. Now what does that do is it sets requires grad true. That means the weights of the vision and image encoder, be it CNN based architecture or transformer based architecture, the weights of the layers are going to be fine-tuned when we actually train the model. Same is the case for the sentence transformer model which we used, where the trainable parameter is set to true, hence the required grad is true. So now why I'm showing this is to quickly drive the point that it is not only merely a joint embedding space, but it also V+L jointly learned space, right? So that's the difference when compared to a traditional unimodal embedding space, right? Okay, now in terms of data set, we are going to visualize the joint embedding space of the model we built using the test slice of the Celebi data set we used in the previous episode, right? So this is where I'm bringing the test slice, and it has got a lot of image description, attribute descriptions of the image here. But as you can see, right, the attribute description says the gender and different facial expressions like smiling, faces open, mouth slightly open, bald, hair, chubby, bangs, and different kinds of expression. We are not going to get into every single attribute for this particular exercise. Let me explain that in a minute, how we are going to actually qualitatively look at the joint embedding space. So these are brass tacks. Now the data set that I've loaded from the test slice is converted into a torch data set, and then I've loaded into a torch data loader. And once that is done, this is the main method that is basically going to use the model that we loaded to embed the text part and the vision part, right? So let me explain. Instead of getting all the individual attributes, let me go back up top, right? So all the individual attributes, if you look at it, that is like we have 40 different attributes, right? And in reality, these 40 different attributes are not used like labels. They are not used as an image with only one label. They are used in combination, right? A single image can have multiple different attributes, right? So for this particular exercise, what I'm going to do is, in this particular method, I'm going to pick up only 3 to 4 text attributes, like standalone attributes, not even combination, and I'm going to use them in tandem with the image embeddings. So the first for loop here is basically using the image encoder portion of our face retrieval network and encodes all the images in the test slice of the database. This for loop is basically using this 4 labels, uses the text encoder part of our model, encodes them and give it back, right? So what I've done is, for each of those, since this is text encoding and this is image encoding, for ease of visualization, I've also have converted these text, right, eyeglasses, the text portion also as images. And if it is confusing to you, hang on with me, I'll explain in a minute. For now, just follow my train of thought. We have image names, we have the image embeddings, and we have the text embeddings. And then using those, this step basically runs the method, and this is basically combining all the image embeddings and text embeddings into one set of embeddings, because we want to project both the image embeddings and test embeddings in the shared embedding space and see how they are located, right? How the model has learned to project them, right? And we want to see how the real estate looks, right? Whether it's 2D or 3D. That's for now. But before that, let's look at a couple of different ways of visualizing. Is obviously we have 2D visualizations, and then obviously we have 3D visualizations, right? Now, if you look at here, what we have done is this visualization is classically called as, in terms of plots, called as a scatter plot, right? The scatter plot is useful in this case because we are taking text data, giving different colors to plot it, right? Let's imagine if you're going to use the same thing, kind of a scatter plot, but not for labeled data set, but in our case, what we have is a celeb photographs, and we have attributes, right? For simplicity, I have done a scatter plot for taking 5,000 records alone from the test slice, and then the labels are only male and female instead of taking all the labels, right? As you can see, you can take some, this is again using UMap. As you can see, right, the lessons are obviously, the intuition basically tells that it is not a classic way of splitting males from females, right? You can see there are males in the other cluster, there are females in the male cluster also. So it basically says the clustering or the split basically happened based on the attributes. It could be male wearing a hat and a female wearing a hat has to stay together, not the other way around, right? So we can get a basic feeling from the scatter plot, but it's really not useful. Even though this is a giant embedding space, it's not really useful in terms of presenting a case to a stakeholder or confirming your intuitions about the model, right? So just want to give you like a very low level vanilla visualization. This is another form of visualization if you want to like combine this embeddings that we have learned from our model, combine that with k-means clustering to see how many clusters are there. So depending on the stakeholder you are looking at, you could say that in these celebrities in our particular data set basically organize themselves into 20 different clusters based on their attributes. It might sound completely an useless exercise for this particular data set, but if you think about different data sets in the embedding space, how data cluster together or organize themselves kind of it might be useful depending on the data set. So this is another way to do it. Again, it is a scatter plot. It has some utility, but again, it is not really a visualization which is very useful for the cell-based data set we have, right? So as you can see, what I'm trying to do is I'm going from simple to complex way, and also I'm trying to demonstrate that what is the best way of, I mean, there are all visualizations are not made equal. Simply looking at a scatter plot for a celebrity image A may not be of high utility, may not be a high utility visualization. So we will also eventually land to a place where a perfect visualization that is useful for this particular data set, right? So the next step is, instead of a scatter plot, we are going to stick to the 2D visualization, but instead of scatter plot, how about we bring the images and the text and we see how it looks, right? And this is the particular cell I'm talking about. We have, as you can see, we have both UMAP option as well as t-SNE option, and I have timed it. It's in the order of seconds. Obviously for UMAP it's pretty fast, but for t-SNE it's in the order of minutes. But you know, if for this exercise, feel free to explore, guys. If you want to check out how t-SNE looks and how is it different from UMAP, feel free to do that. So long story short, what I've done is, since it is not a scatter plot, we want to obviously take the images and encode it so that we can plot it in the 2D plot itself. The image is going to be, so if you're not sure as to what I'm trying to say here, if you look at this, right, this is what we are trying to build, right? Meaning what I'm trying to do here is take the photographs and encode it in some way, shape or form, and in the same scatter plot, 2D scatter plot, plot them along with the text embeddings. As you can see, there is eyeglasses here and there is a wearing hat here, right? So let's get, this is the actual outcome we are trying to look at from this cell. Let me go back and explain this, right? So to get that particular output, we need the images. So this particular cell, what it does is, there are a couple of different ways you can encode the image. One way is to do the URA encoding. That's what we are basically, base 64 base URA encoding is what I'm doing here, right? So it not only encodes the images of the actual celebrity faces, it also takes the images of the labels that we created, right? That is black hair and wearing hat and things like that. So that's what is happening, and the library of our choice is Plotly. By no stretch of imagination, I'm an expert in this library. I've just Googled and taken the code for scatter plot. So again, here for simplicity, I've taken only 2000 records from the test slice, and the first part that I'm highlighting is actually plotting the scatter plot. It works in a couple of different ways, right? Even though we are plotting the actual image, for us to have a better visualization in the 2D scenario, we have to come up with the scatter plot. On top of those scattered dots, we have to populate the images. And that's what the second step is doing, right? Once you come up with the scatter, the add layout image is basically going to put those images on top of it, so it is visually appealing and it's easy for you to reason with it and compare with your intuition and so on and so forth. So that's what is happening here, and that produces this particular result, right? So if you look at this, let me go back. Just give me 1 second. So now if you go back here, As you can see, the images are organized in the two-dimensional space. We have done a nice scatter plot. We have populated the images, and as you can see, we also have the text version, the images of the text labels, right? For ease of use and for simplicity, instead of populating images and text, it is easy for us to converting everything into image. So what I've done is, for the label wearing hat, I've created an image which says wearing hat, and I've also populated that as image, but the wearing hat's position is encoded by the text encoder. I hope you understand. What I've done is, wearing hat is a label that will be encoded by the text encoder part of the model. All the images are encoded by the image encoder part of the model. But for us to visualize easily, I've taken the label, created an image out of it, and then populated in the scatter plot as the image, right? So as you can see, right, all the people who are wearing hats or some kind of headgear are populated near that wearing hat. I have not populated the wearing hat label here. It is the automatic embedding of both the text and the images, which are just visualized in the scatter plot. And here you can see all the people with eyeglasses and the eyeglasses labels embedding, and the images are all together, right? So I mean, I'm not going to obviously get into obvious, so there is mustache here and this distance, but one thing you could notice, right? The mustache guys, the guys with mustache and the actual mustache label is slightly farther. That's where this whole thing comes in, right? When you are doing two-dimensional, one of the dimensions is completely compressed. You don't get the depth of how far these labels are. That's where visualizing this, even though it is much more better than a simple dots in a scatter plot, it is still having some problems, or it is having some issues because you miss the actual depth. That's where we are going to look at 3D. So before going to three-dimensional plots, let me share a couple of things, guys. The main thing about this particular cell is, even though it is visually appealing and all, I've used only 2000 images for a reason, because this add layout image, which basically replaces the scatter plot marker with the images, is painfully slow. And if you can afford more time, and if you can run this in the background, bring more images and bring more labels, and feel free to experiment. That's something I wanted to say here. And obviously the next step is visualizing using 3D, visualizing the same embeddings in a 3D three dimensions, right? So the main thing that you want to take away here is, as you can see before, we have taken the raw embeddings and we used certain external libraries for coming up with the UMAP or TSNE embeddings, right? But here the good thing is, I'm going to directly borrow TensorBoard, which does the heavy lifting for us, which means, excuse me, we can directly use the raw embeddings and it can do UMAP, TSNE, PCA and other things for us. Plus it can give a very visually appealing aesthetic 3D representation of our data. Again, by no stretch of imagination, I'm a TensorBoard expert. Feel free to run your fingers around Google. You will find a lot of examples. So these are pretty straightforward 3 cells, which tells you how do you instantiate TensorBoard and how do we have to resize. I mean, for instance, one of the important things that you need to keep in mind is, for projecting images, it's better if you bring those images really down, like 28 by 28. Our standard images are 224 by 224, pretty large for a 3-dimensional dimension projection, right? And this is the step which basically takes the raw embeddings and projects it to our TensorBoard embedding space. I'll show that in a minute. And so there are a couple of different ways, and this is the fancier default version. As soon as you bring the projection tab, it shows the PCA version of it. And as you can see in the bottom, the PCA version captures only bare minimum variance in the data. And obviously PCA is not suitable for multiple reasons. One of it is, if all the variance is captured by the top 3 or top 1 or 2 principal components, then it is a best fit. And also it's a linear projection technique, right? Linear dimensionality reduction technique. So it's better to use a dimensionality reduction technique that best serves for our purposes. As you can see, like I said before, TensorBoard has this UMAP, TSNE and PCA options where you can run PCA version or TSNE version and stuff like that, right? So this is the this is the TCNE version. Let me just go back to the UMAP version of it. Again, right, feel free to run whichever version that makes sense to you guys. The main thing that I want to show here is, guys, like when I showed the UMAP version, the 2D UMAP version where the photographs are there, I said the depth is missing and we are not able to reason about it in the way we actually wanted to, right? So I wanted to show like the same UMAP, instead of 2D, we have that extra depth of the third dimension is here, right? So let's go ahead and search for one of the labels which we are interested in, and as you can see, right, so I want to give you a fair warning, guys. This is very cursor sensitive, the zoom in and zoom out. I'm trying my best to show you guys, but I think the best course of action is for you is to once I give the notebooks, take the notebooks and do it for yourself. But if you see what I'm trying to show is how it is advantageous once you have access to these eyeglasses. You can search fortunately for the, so yeah, so this eyeglasses.jpg is the image that we are interested in, which is basically the image of the label, and you can see in the neighborhood we have all the people who are wearing some form of eyeglasses or eyewear. The main thing that you want to notice is the depth, right? So all of them are not flatly available in the same level. Why? Because eyeglasses is one of the common factors, but it is not the common, it is not all the common factors, right? Because we have several different attributes bringing these people together, and the differences in the attributes actually separates them in terms of distance, right? So that's what this is showing, and then we can try maybe one more example where I can say wearing hat. If I search that, yeah, wearing hat is somewhere around here. As you guys can see, all the people wearing hat are kind of in the same vicinity, but still there is some difference in the depth because they are not together only because of they are wearing hat. There are some difference. For example, men wearing hat with mustache are slightly further away from people who are clean shaved. I mean, feel free to explore this, guys. And the right pane, I'm sorry it is not very clear, but the half showing the right pane basically shows you when you click an image, it shows you the nearest points, either based on cosine distance or Euclidean distance, nearest first, right? So yeah, the main point that I want to drive here is that extra depth is giving you some advantage in visualizing the data, right? So that's pretty much what I wanted to cover, guys, and in this episode. And so I'll, as usual, in terms of brass tacks, I'll give the link to the notebook in the description, and probably I'll also give the link to the UMAP resource I shared. So feel free to check it out, and thanks for your time. Cheers.